Point 2. Express each number as a product of its prime factors. Number 1. 140. Solution. Using factor 3 method, we have factors of 140 are 2 and 70. Further, factors of 70 are 2 and 35. Factors of 35 are 5 and 7. Since 2, 5 and 7 are prime numbers, therefore 140 is equal to 2 into 5 into 7. Therefore 140 is equal to 2 square into 5 into 7. Number 2. 156. Solution. Using factor 3 method, we have factors of 156 are 2 and 78. Factors of 78 are 2 and 39. Factors of 39 are 3 and 13. Therefore, 156 is equal to 2 into 2 into 3 into 13, which is 2 square into 3 into 13. Number 3. 3825. Solution. Using factor 3 method, we have 3825, where factors are 3 and 1275. Factors of 1275 are 3 and 425. Factors of 425 are 5 and 85. Factors of 85 are 5 and 17. Since 3, 5 and 17 are all prime numbers, therefore 3825 is equal to 3 into 3 into 5 into 5 into 17. That is 3 square into 5 square into 17. Number 4. 5005. Solution. Using factor 3 method, we have factors of 5005 are 5 into 1001. Factors of 1001 are 7 and 143. Factors of 143 are 11 and 13. Therefore, 5005 is equal to 5 into 7 into 11 into 13. Number 5. 7429. Solution. Using the factor 3 method, we have factors of 7429 are 17 and 437. Further, factors of 437 are 19 and 23. 17, 19 and 23 are all prime numbers. Therefore, 7,429 is equal to 17 into 19 into 23. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of the two numbers. Number 1, 26 into 91. Solution. Using factor tree method, we have factors of 26 are 2 and 13. Factors of 91 are 7 and 13. So 26 is equal to 2 into 13. So 91 is equal to 7 into 13. Therefore, LCM of 26 and 91 is equal to 2 into 7 into 13, that is 182. HCF of 26 and 91 is 13. Now, LCM into HCF is 182 into 13, that is 2366, and 26 to 91 is 2366. That is, LCM into HCF is equal to product of two numbers. Number 2, 510 and 92. Solution. Using factor tree method, we have factors of 510 are 2 and 255. Factors of 255 are 5 and 51. Factors of 51 are 3 and 17. Now, factors of 92 are 2 and 46. Factors of 46 are 2 and 23. So 510 is equal to 2 into 5 into 3 into 17. So 92 is equal to 2 into 2 into 23. Now LCM of 510 and 92 is equal to 2 into 3 into 5 into 17 into 2 into 23. That is 23,460. HCF of 510 and 92 is 2. So, LCM into HCF is 23,460 into 2. That is 46,920. And 510 into 92 is 46,920. That is, LCM into HCF is equal to product of two numbers. Number 3, 336 and 54. Solution. Using factor tree method, we have factors of 336 are 2 and 168. Further, factors of 168 are 2 and 84. Factors of 84 are 2 and 42. Factors of 42 are 2 and 21. And last, factors of 21 are 3 and 7. Now let us see the factorization of 54. Factors of 54 are 2 and 27. Factors of 27 are 3 and 9. Factors of 9 are 3 and 3. Therefore, 336 is equal to 2 into 2 into 2 into 2 into 3 into 7. And 54 is equal to 2 into 3 into 3 into 3. LCM of 336 and 54 is equal to 2 into 2 into 2 into 2 into 3 into 3 into 3 into 7. That is 3024. HCF of 336 and 54 is equal to 2 into 3, that is 6. LCM into HCF is equal to 3024 into 6, that is 18,144. Also, 336 into 54 is equal to 18,144. Thus, LCM into HCF is equal to product of the numbers. Find the LCM and HCF of the following integers by applying the prime factorization method. Number 1, 12, 15 and 21. Answer. We have 12, 15 and 21. 12 is 2 square into 3. 15 is 3 into 5. And 21 is 3 into 7. Now highest common factor is 3. LCM would be 2 square into 3 into 5 into 7. That is 420. Number 2, 17, 23 and 29. Solution. Here we have factors of 17 are 1 into 17. Factors of 23, 1 into 23. Factors of 29, 1 into 29. 17 are 1 into 17. 23, 1 into 23. 29, 1 into 29. HCF of 17, 23 and 29 is 1. LCM of 17, 23 and 29 is 17 into 23 into 29. That is 11,339. Number 3, 8, 9 and 25. Solution. Now we have factors of 8 are 2 and 4. Factors of 4 are 2 and 2. Factors of 9 are 3 and 3. Factors of 25 are 5 into 5. So 8 is equal to 2 into 2 into 2. So 9 is equal to 3 into 3. So 25 is 5 into 5. Therefore, HCF of 8, 9 and 25 is 1. LCM of 8, 9 and 25 is 2 into 2 into 2 into 3 into 3 into 5 into 5 or 1800. Check whether 6 raised to power n can end with the digit. Given that HCF of 306 and 657 is 9. Find LCM of 306 and 657. Answer. We know that HCF of 306 and 657 is 9. Well, you already know that LCM into HCF is equal to product of two numbers. Therefore, LCM into HCF is equal to 306 into 657. So LCM would be 306 into 657 upon HCF, that is 306 into 657 upon 9. So LCM is 22,338. Check whether 6 raised to power n can end with the digit 0 for any natural number n. Solution. Here n is a natural number and let 6 raised to power n end in 0. Therefore, 6 raised to power n is divisible by 5. But the prime factors of 6 are 2 and 3. So 6 raised to power n would be 2 into 3 whole raised to power n. That is, in the prime factorization of 6 raised to power n, there is no factor 5. Since by the fundamental theorem of arithmetic, every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factorization occurs. Therefore, our assumption that 6 raised to power n ends in 0 is wrong. Thus, there does not exist any natural number n for which 6 raised to power n ends with 0. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Solution. We have 7 into 11 into 13 plus 13 is equal to 13 into 7 into 11 plus 1, which is 13 into 78. That is, 13 into 78 cannot be a prime number because it has a factor 13. Therefore, 13 into 78 is a composite number. Also, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is equal to 5 into 7 into 6 into 4 into 3 into 2 into 1 plus 1, which is also not a prime number, since it has a factor 5. Thus, 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. There is a circular path around the sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Solution. Time taken by Sonia to drive one round of the field is 18 minutes. Time taken by Ravi to arrive one round of the field, 12 minutes. The LCM of 18 and 12 gives the exact number of minutes after which they meet at the starting point again. We have factors of 18 are 2 and 9. Factors of 9 are 3 and 3. Factors of 12 are 2 and 6. Factors of 6 are 2 and 3. So 18 is equal to 2 into 3 into 3 and 12 is equal to 2 into 2 into 3. Therefore, LCM of 18 and 12 are 2 into 2 into 3 into 3, that is 36. Thus, they will meet again at the starting point after 36 minutes. Exercise 1.3. Prove that root 5 is irrational. Solution. Let root 5 be a rational number. Therefore, we have to find two integers a and b, where b is not equal to 0 and a and b are co-prime such that a upon b is equal to root 5. So a is root 5 into b. Let us put it as 1. Squaring both sides, we have a square is equal to 5 into b square. Therefore, 5 divides a square. So 5 divides a. Let us put it as 2. Since a prime number p divides a square, then p divides a, where a is a positive integer. Therefore, a is 5c, where c is an integer. Therefore, putting a is equal to 5c in 1, we have 5c is equal to root 5b, or 5c whole square is equal to 5b square. So 25c square is equal to 5b square. So 5c square is equal to b square. So 5 divides b square, which means 5 divides b. Let us put it as 3. From 2 and 3, a and b have at least 5 as a common factor. That is, a and b are not co-prime. Therefore, our supposition that root 5 is rational is wrong. Hence, root 5 is irrational. Prove that 3 plus 2 root 5 is irrational. Solution. Let 3 plus 2 root 5 is rational. Therefore, we can find two co-prime integers a and b such that 3 plus 2 root 5 is equal to a upon b, where b is not equal to 0. Therefore, a upon b minus 3 is equal to 2 root 5. So, a minus 3b upon b is equal to 2 root 5. So, a minus 3b upon 2b is equal to root 5. Let us put it as 1. Since a and b are integers, so a minus 3b upon 2b is equal to integer minus 3 into integer upon 2 into integer. So, a minus 3b upon 2b is equal to rational number. So 1 is irrational, which means root 5 is irrational. But this contradicts the fact that root 5 is irrational. Therefore, our supposition is wrong. So 3 plus 2 root 5 is an irrational. Prove that the following are irrationals. Number 1. 1 upon root 2. Solution. We have 1 upon root 2. It is equal to 1 upon root 2 into root 2 upon root 2. That is root 2 upon 2. That is 1 upon 2 into root 2. Let 1 upon root 2 be rational. And 1 upon root 2 is equal to 1 upon 2 into root 2. Therefore, 1 upon 2 into root 2 is irrational. Let 1 upon 2 into root 2 is equal to a upon b, such that a and b are co-prime integers and b is not equal to 0. Therefore, root 2 is equal to 2a upon b. Let us put it as 1. Since the division of two integers is rational, therefore 2a upon b is irrational. From 1, root 2 is a rational number, which contradicts the fact that root 2 is irrational. Therefore, our assumption is wrong. Thus, 1 upon root 2 is irrational. Number 2. 7 root 5. Solution. Let us suppose that 7 root 5 is rational. Let there be two co-prime integers a and b, such that 7 root 5 is equal to a upon b, where b is not equal to 0. Now, 7 root 5 is equal to a upon b. Root 5 is equal to a upon 7b, that is integer upon 7 into integer, which is equal to rational. So, root 5 is irrational. This contradicts the fact that root 5 is irrational. Therefore, we conclude that 7 root 5 is irrational. Number 3. 6 plus root 2. Answer. Let 6 plus root 2 be rational. Therefore, we can find two integers a and b which are not equal to 0 such that 6 plus root 2 is equal to a upon b. Root 2 is equal to a upon b minus 6. Since a and b are integers, a upon b minus 6 is also rational. Hence, root 2 should be rational. This contradicts the fact that root 2 is irrational. Therefore, our assumption is false. Hence, 6 plus root 2 is irrational. Exercise 1.4. Without actually performing the long division, state whether the following rational number will have terminating decimal expansion or a non-terminating repeating decimal expansion. Number 1. 13 upon 3125. Answer. Well, 3125 is equal to 5 raised to power 5. The denominator is in the form of 5 raised to power m. Hence, the decimal expansion of 13 upon 3125 is terminating. Number 2. 17 upon 8. Solution. Now here we have 17 upon 8. Since 8 is equal to 2 into 2 into 2, that is 2 cube, which is equal to 1 into 2 cube, so it is 5 raised to power 0 into 2 cube, which is of the form 5 raised to power m into 2 raised to power n. Therefore, 17 upon 8 will have terminating decimal expansion. Number 3. 64 upon 455. Answer. Well, Factorization of 455 is 5 into 7 into 13. Since the denominator is not in the form of 2 raised to power m into 5 raised to power n, and it also contains 7 and 13 as its factors, decimal expansion of 64 upon 455 will be non-terminating repeating. Number 4. 15 upon 1600. Answer. Well, factorization of 1600 is 2 raised to power 6 into 5 square. Now the denominator is in the form of 2 raised to power m into 5 raised to power n. Hence the decimal expansion of 15 upon 1600 is terminating. Number 5. 29 upon 343. Solution. We have 29 upon 343. Since 343 is equal to 7 into 7 into 7, that is 7 cube, which is not of the form 2 raised to power n into 5 raised to power m. Therefore, 29 upon 343 will have a non-terminating repeating decimal expansion. Number 6. 23 upon 2 cube into 5 square. Solution. Let P upon Q is equal to 23 upon 2 cube into 5 square. That is, Q is 2 cube into 5 square, which is of the form 2 raised to power n into 5 raised to power m. Therefore, 23 upon 2 cube into 5 square will have terminating decimal expansion. Number 7. 129 upon 2 square into 5 raised to power 7 into 7 raised to power 5. Answer. Now since the denominator is not in the form of 2 raised to power m into 5 raised to power n, and it also has 7 as its factor, the decimal expansion of 129 upon 2 square into 5 raised to power 7 into 7 raised to power 5 is non-terminating repeating. Number 8. 6 upon 15. Answer. Now here the decimal expansion is 2 into 3 upon 3 into 5. That is 2 upon 5. Now the denominator is in the form of 5 raised to power n. Hence the decimal expansion of 6 upon 15 is terminating. Number 9. 35 upon 50. Answer. Well, factorization would be 7 into 5 upon 10 into 5. That is 7 upon 10. 10 is equal to 2 into 5. Now, here the denominator is in the form of 2 raised to power m into 5 raised to power n. Hence, the decimal expansion of 35 upon 50 is terminating. Number 10. 77 upon 210. Answer. Here, after factorization, 77 upon 210 would be 11 into 7 upon 30 into 7. That is 11 upon 30. Now 30 is further equal to 2 into 3 into 5. Since the denominator is not in the form of 2 raised to power m into 5 raised to power n, and it also has 3 as its factor, the decimal expansion of 77 upon 210 is non-terminating repeating. Write down the decimal expansions of those rational numbers in question 1 above, which have terminating decimal expansions. Number 1. 13 upon 3125. Answer. Now we have 13 upon 3125. If you factorize the numerator and denominator, it is 13 upon 5 into 5 into 5 into 5 into 5, which is 13 upon 5 raised to power 5. Multiplying and dividing by 2 raised to power 5, we have 13 upon 3125 equal to 13 upon 5 raised to power 5 into 2 raised to power 5 upon 2 raised to power 5. Now, it is equal to 13 into 32 upon 10 raised to power 5. That is 416 upon 10 raised to power 5, which means it is 0.00416. Number 2, 17 upon 8. Solution. 17 upon 8. Now 17 upon 8 is equal to 17 upon 2 into 2 into 2. That is 17 upon 2 cube. In order to rationalize the denominator, let us multiply and divide by 5 raised to power 3. So 17 upon 8 is equal to 17 upon 2 cube into 5 cube upon 5 cube, which is 17 into 125 upon 10 cube. That is 2125 upon 1000, which is 2.125. Number 3. 64 upon 455. Answer. 64 upon 455. Well, this represents non-terminating repeating decimal expansion. Number 4. 15 upon 1600. Answer. If we factorize 15 upon 1600, it is 15 upon 2 into 2 into 2 into 2 into 10 into 10. So it is 15 upon 2 raised to power 4 into 10 square. Let us multiply and divide it by 5 raised to power 4. So 15 upon 1600 is equal to 15 into 5 raised to power 4 upon 2 raised to power 4 into 5 raised to power 4 into 10 square. So it is 15 into 625 upon 10 raised to power 4 into 10 square. So it is 9375 upon 10 raised to power 6, which means it is 0.009375. Number 5. 29 upon 343. Answer. 29 upon 343 represents a non-terminating repeating decimal expansion. Number 6. 23 upon 2 cube into 5 square. Solution. 23 upon 2 cube into 5 square. Now we have 23 upon 2 cube into 5 square. It would be 23 into 5 upon 2 cube into 5 square into 5, as we will multiply the numerator and denominator by 5. So it is 115 upon 2 cube into 5 cube, which means it is 115 upon 10 cube, that is 0.115. Number 7. 129 upon 2 square into 5 raised to power 7 into 7 raised to power 5. Answer. 129 upon 2 square into 5 raised to power 7 into 7 raised to power 5 represents a non-terminating repeating decimal expansion. Number 8. 6 upon 15. Solution. Now, 6 upon 15 is equal to 2 upon 5. So here we will multiply numerator and denominator by 2. So it is 2 upon 5 into 2 upon 2, that is 4 upon 10, which means it is 0.4. Number 9. 35 upon 15. Answer. Now 35 upon 50 is 7 upon 10, that is 0.7. Number 10. 77 upon 210. Answer. 77 upon 210. It represents a non-terminating repeating decimal expansion. The following real numbers have decimal expansions as given below. In each case, decide whether they are rational or not. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? Number 1. 43.12345678 Solution. Now here we have 43.12345678. Since the given decimal expansion terminates, therefore it is a rational of the form P upon Q. So P upon Q is equal to 43.12345678. So it is equal to 4312345678 upon 100000000, which is equal to 4312345678 upon 10 raised to power 9, which is further equal to 4312345678 upon 5 raised to power 9 into 2 raised to power 9. Here P is 4312345678 and Q is 2 raised to power 9 into 5 raised to power 9. Therefore, prime factors of Q are 2 raised to power 9 and 5 raised to power 9. Number 2. 0.120, 1200, 12000, 1200000, so on. Answer. 0.120, 1200, 12000, 1200000, so on. Now here, the decimal expansion is neither terminating nor recurring. Therefore, the given number is an irrational number. Number 3. 43.12345678 bar. Solution. Now here we have 43.12345678 bar. Since the given decimal expansion is non-terminating repeating, therefore it is a rational number. Let P upon Q is equal to X, which is equal to 43.12345678 so on. Let us put it as 1. Multiplying both sides by 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, we have 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 into x is equal to 4, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let us put it as 2. Subtracting 1 from 2 we have 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 into x minus x is equal to 4, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 minus 43.123456789. So it is 99999999 x is equal to 431234564746. So x is equal to 431234564746 upon 999999999, which is equal to 143,744,855,82 upon 33,33,33,333, which is further equal to 479,1495,194 upon 11,11,11,111, which is equal to P upon Q. Here P is 4791495194 and Q is 11,11,11,111, which is not of form 2 raised to power n into 5 raised to power m. That is, the prime factors of Q are not of form 2 raised to power n into 5 raised to power m.